So, why I'm talking about functional programming? You know templates in C++, you know template metaprogramming, and then you know nothing. Because you have to have an idea of functional programming about the ideas. And then maybe you have an idea how template metaprogramming should work at compile time. And that was the starting point for me to think a little bit about the functional programming paradigm. So, what I will talk about is about programming in a functional style. You know, C++ is not a functional language, of course, but you can program in a functional style. Then I say, why functional programming? Why should you care? Then, what is functional programming? And that point is a little bit difficult to get. So, I give you a few characteristics of functional programming. So, class functions, after functions, core functions. And that's only my point of view. And now I say what's missing, and you know what I'm missing, what's still missing in C++. I will give a lot of code examples in Haskell, which is a functional language, in Python, which supports a lot of functional features, and of course in C++11. Let's start. So, you can program in a functional style in C++11. As you noticed it from yesterday, the functional paradigm is extremely important in C++11. Mike emphasized it. What you can do in C++ is auto decking type. This is automatic type deduction, also known in Haskell. Now you can do it in C++. You have something like lambda functions, of course, from the functional world. Lambda functions which can capture the environment, though there are also closures. And what's great about lambda functions, they are like data. These are first-class functions, so you can copy them, you can bind them to data, and so on. Extremely convenient. Then you have something like partial function application. I showed the example yesterday, but I will show also one today. That's similar to Turing in Haskell. And you know, Turing is called Turing because the man who gives the name to it is called Haskell Turing. Or Turing Haskell, I don't know. It doesn't matter. Standard functions, standard binds, you can do it with threading, with the STL capabilities, but you can also do it with the core language using lambda functions and auto. Then you have something like higher order functions. That these are functions which can accept functions and can return functions. These are higher order functions. Then you have something similar. That's the reason for writing it a little bit different, like list manipulation, which is extremely characteristic of functional languages. You can do it if you like it in variable templates. I emphasize if you like it. Then, you have general templates, you have fully partialized templates, you have totally defined templates, or I missed the point a little bit. But you have something like pattern matching available with templates. That one is also available in functional languages like Haskell. Then a little bit of lazy evaluation, like standard async. That means the result you will get only the result if you actually need it. That's lazy evaluation. Do it as late as possible. Maybe you haven't to do it. And you know the discussion about concepts. Concepts may be called constraint template in the new C++ 22 standard. And the idea of concepts comes from Haskell. In Haskell it's called type classes, and that's a great feature. Having something like a type system for templates. So, why functional programming? Of course, you can use the STL more effectively. Have a look here. I think that looks great. One line, the whole expression, and what this line will do is add together all numbers beginning at the begin and ending at the end. And the result is of course the sum of the number. Another reason for thinking about functional programming Tensor meta programming. You have an idea to recognize the pattern, because these are functional patterns, you know? I will explain this function a little bit later in more detail, but this is a function. A template meta function means it will be evaluated in compile time, and you see it here, that's the general case, and that's the end condition, and that function will be evaluated in compile time, and at runtime you will get the value. Maybe back of 5 is 120. Why functional programming? I think it's a better programming style, because you begin to think or to reason about side effects. What's the good, what's the bad function, what's the global state, what you should change. So it's a kind of you learn to program in a better way. And also, of course, it's more concise. Look at the auto, I like it, in a range-based look. These are only 3 points. I think you can mention 10 of them. Then, what is functional programming? The definition is extremely simple, but it will not help. Functional programming is programming with mathematical functions. That's the definition. That's all. But a mathematical function is a function that each time returns the same value when given the same argument or arguments. That means referential transparency. Think a little bit about it. There are a lot of consequences involved. At first, functions are not allowed to have side effects. One consequence. It's a sentence. The function invocation can be replaced by the results. In case you invoke a function 10 times with the same argument, you have only to do it once, and the rest you have to result. Then the optimizer is allowed to rearrange functions, because the functions are independent of their environment. So he can rearrange it, or he can perform it on a different thread. Doesn't matter. Automatically. And that's the key point, I think, about functional programming. The program flow will be driven by data dependencies and not by sequences of instructions. Because it doesn't matter what sequence of instructions will actually take place. So, but to give you a better idea of what functional programming is, I look at six characteristics of functional programming, and I show you a lot of examples concerning these 6 characteristics. Good. First class functions, ion functions, you will see. At first class functions. First class functions are functions that behave like data. As mentioned before, you can copy it, you can bind it to variables, you can pass it as arguments to other functions, you can return it from functions. We have them still in C++. Maybe you'll see we have function pointer in C++, we have function objects, what are called functors, and now you have lambda functions. See, the things behave like data. Here, look at my example, I use it here. I make a simple dispatch table using the new C++ capabilities. I did that maybe 10 years ago with templates that was horrible. Now we can do it in an extremely elegant way. At first, I create a map. You see it? The key, the constraint, the value is a function record. You see it? The value is a function record taking 2 doubles and returning in double. You get it? Then I register different function objects. This is the key. Plus and the operation is a lambda function which will exactly do that, adding 2 arguments. I do it for plus, I do it for minus, times and division. And then here I can apply it. That was all. Tab of plus will return a function object, that's that guy, and that guy I will invoke with these arguments, and I think you will believe me that is the right result. Extremely convenient. I can do it also for something like times. But oh, I forget to add the power function. I can add it afterwards. You see? I copy the lambda function like data and bind it in the table, in my dispatch table. And you see also I used, of course, lambda function. That's not necessary. I can also use function or function objects, but I will do it with lambda functions. Because we are here to learn C++11. First class functions. You know the three guys, they are important, but as maybe not so important like these three functions, which are the most. Don't believe me? Say we will go longer. These are the three most important higher order functions. Map, filter, and fold. Higher order functions are functions. Stop to laugh, I have to concentrate myself. Higher order functions are functions which can accept other functions' arguments or return them. This is a higher order function. A simple concept. The three guys here, map, apply a function to each element of the list. Think about a list like a sequence of elements of the same type. Apply a function to each element of the list, filter, remove an element from a list, and returning, of course, the modified list. And then it's a little bit more complicated for it. Reduce the list to a single value by successively applying a binary operation. That means, in the first case, you have an initial value in your left hand, the first value of the list. Then you apply the binary operation, maybe plus, you add it. 0 plus 1 is 1, you have 1. The next step, you get the second element from the list. 1 plus 2 is 3. The next step, 3 plus 4 is. So you apply and you fold it, and it will return one value. So, because these three guys are so important, each programming language, I hope it will be true, that will support programming in a function that has to support these three functions. Here, that's the name for these three functions in Haskell, map, filter, and here it's called fold. With an asterisk because there are 4 different versions available in Haskell, because it's so important. Then in Python, who knows Python here? Oh, good. You can, so in my next example, you can look at the Python code if you don't like Haskell. If you don't like Haskell, of course, then you can look.
Yes. And I will say later that Ruby is much better than Python.
You have to prove it, it's only a statement. You see, map, filter, reduce, that's the same in Python. And in C++, you have transform, remove it, and accumulate. These are the corresponding functions in C++11. Never forget about C++11, C++, of course. Then have a look. In case you add map introduce, you make a little bit string concatenation and you see what you will get. Map reduce. And that's the reason for the name of this big framework, which is well known. So you can, these ideas are extremely important. Now I show you a few examples. Only for the start, I always use in Haskell a list beginning at 1 and ending at 9. The same in Python, the same in C++, but I use a vector. In Haskell here I'm using a string consisting of words, only to show you once what I will use in the next slides. So, map, as I mentioned before, that's the Haskell implementation. Maps applies a function to each element of a list and will return a new list. So I apply A should be mapped to A times A on the vector back, on the list back. You don't have to use brackets in Haskell. Then I apply A to length A. So I want to know the length of each word. I apply it to a vector and I apply it to the list. If you like Python, that's the same. If you like C++11, That's the same code in C++11. Back begin to back end, store the result at back begin and apply this lambda function to it. And here apply the length function to it. And that will be the result in a language independent way. That's all. These along two are the length of the words from before. I think programming in a functional style was missing, was missed of the words. So, filter, next. Filter applies a filter to each element of a list and that gives you back in Haskell a new list only having this mentioned filter. Here I'm interested only in values which are smaller than x, smaller than 3 or bigger than 8. Here, that's a little bit difficult to read. A head of x will give you the first element of the string. The string is maybe programming and you will get P, big P, P will be big in capital letter. And I'm asking for, is it upper? So I only want to have the words which the first letters written with the uppercase. That's my filter. That's Haskell, that's Python, that's C++. I think that looks extremely convenient in C++. And now you get it, 1 to 9, because 1, 2, and 9 are still fulfilled or filtered. And now the last guy, which is understood the most powerful one of these three, but a bit difficult to get. For it, I used the version 0.L in Haskell. What it will do, it will successively iterate. Wait a second, I will explain a second example and you can guess from the solution what it will do. Here, so it will iterate to the whole vector or list of words and concatenate each word with a colon symbol. The starting point is an empty string. You have to give a starting point because that's the initial, and that is the list of words I want to concatenate. Have a look here. Starting point, then empty string, x plus colon is colon, then programming. And here, you know what this is? Who has the answer? What's that? For the multiplication of the elements of the factorial of 10. You have to know it by heart. Sorry. But you see, I can write faculty in different, of course, in different way. You will see it in 3 or 4 different forms. The next slide. Good. The next big characteristic of functional programming are pure functions. This is from the book Grimm about Haskell, and pure functions are functions which always produce the same result when given the same parameters, never have side effects, never either state. That's the key point of pure functions. Pure. So, pure functions are isolated. The program is easier to reason about because you know the functions are totally isolated. There's no state involved in something like that. So you can more easily refactor them and test them, because for testing you have to, maybe you have to build a state. So let us test one. So, and that's also a great opportunity for optimization, meaning saving results of pure function invocation. You can do it because you know else you will always give the same result, and you can reward the pure functions or perform it on different threads. We know it from before. But that's only a simple idea, but the implications are enormous. Then, you know, since pure functions has a big problem, the world is impure. I'm only talking in a Haskell way. The world is impure. That means your computer or your program has to deal with the outside impure world. And for doing that, Haskell introduced a concept of monads. I will only give you an idea. And what does it mean? In a monad, you encapsulate the impure world in Haskell because you have a pure language. and you have the impure world, which is not under your control, so you have to encapsulate it. It's like a sandbox. In this subsystem, the imperative rules are the one you have to follow. In this structure, some kind of computation has to be defined, and also the computation of computations. And so there exist a lot of different monads to encapsulate this specific kind of impure world. There's a monad for I/O. There's a monad for maybe. Maybe, of course, if you ask this generally for a value, sometimes you get something, sometimes you get nothing. So your answer is maybe. That's the IO monad. List monad, you know the list. A list can consist of 0 or more valid values, so that's undefined, impure. So you have a monad. You have a state monad for dealing with state. In case you have something like storing a dice, that's impure, or asking for the time, that's impure because each time you invoke a function called time, you will get a different result that will not work, so you have to encapsulate it. And also STM, software actual manual, is actually encapsulated in a monad. So that was all about monads, of course. Recursion, another key concept in functional programming. I will explain the stuff about a little bit later. What's essential about functional programming is, in interactive programming, your control structure are things like for loop, while, and something like that. And to make that happen, you have to have something like state, like variables, which you can change. But that will not be, that is not possible or not available in Haskell. So you have only, it sounds nice, immutable variables. So that about immutable variables. So what you have to do is, instead of looping, you apply recursion. And you can, so you can do the same in a different way. So in case you would combine recursion with this processing, that is a powerful pattern in functional language. I showed the next slide, I hope. Yeah. You see it here in Haskell and you see it in C++. That's the next kind of factorial function. You see, here I'm defining a factorial function. Of course, the factorial of 0 is 1. I hope it should be right. And the factorial of n is n times factorial minus n minus 1. I think that's trivial. Here I define the factorial function in Haskell, recursive anyway, without variables and something like that. And here I do it the same in standard meta programming. That's a function which will be evaluated at compile time, so class standard. You see it here. That's the general case. Fact of 5 equal to 5 times fact of 5 minus 1. And then it will iterate, and here you see the end condition. In case of 0, I get 1. And now you see what will happen at compile time. Fact of 5 will be 5 times fact of 4, will be 5 times 5, 4 times 1. You see it. That will happen at compile time. So, and as I mentioned before, recursion in this compression, you have to, this processing, you have to fit together very well. And you know what will happen in case you read the red letters? That's the reason, you know it. I don't, you know. So, this processing is a characteristic of functional programming. That means transforming a list into a different list, another list, reducing a list to a value, or combining lists. It's all about lists. I show you 2 examples in Haskell, and I give you an idea of that stuff in Python using, in C++ using variable templates. So pattern of processing a list is relatively straightforward in a functional language. You do some action for the head, that means the first element of the list, and you recursively do the same action for the tail of the rest of the list, which is the rest of the list. And because the list is has only a discrete number of arguments, it will end. Have a look here. I want to define a function which will calculate me the sum of the list, my sum. The sum of an empty list, of course, is empty. And the sum of a list consisting of at least one argument, that's the key point, one argument, that's pattern matching, is the first one and the sum of the rest. That's all. And here I apply it. Once more, I do the same for my map. I want to apply a function f to a list, map it on the list, do it on the empty list, of course it's the empty list, because what should I do instead of that? Doing it on the list consisting of at least one argument is doing it in the first argument and doing it once more on the rest of the list. X is the first, xs is always something like more than one. The rest. This column is only a sign for denoting that we create here another list in place. And then my map, you can see it, I apply x will be mapped to x times x on 1, 2, 3, and I will get 1, 4, 9. If you don't like it, then you have to like that stuff. That's the same. Using variable templates, using template encoding. Here's the general case. I'm using a variable template. This my structure can accept arbitrary number of ints. That's the case if I that's the end condition, the empty variable template, and the value of the empty my sum of the empty variable template should of course be 0, and that's the recursion. Do it here, that's the first element, that's the rest, head and tail in Haskell or in functional languages. Then get the value by getting the first element and adding the rest of the list recursively. And then you will get 15. 2 years ago, I tried to implement the map function also at compile time. You can look at it at the link, and I don't want to show you to you, really. It's so good. But you can use it. So my method I wrote at compile time, using meta functions and that's cool stuff. Once more, what's the key difference between list processing in Python and pattern matching in templates is in Python, and sorry, in Python, forget about it, in Haskell, you have something like first match. In C++, you have something like best match. Here, I'm defining a function which should multiply two values, two ints, maybe. I will get the result of 3 times 2 and the result of 46. I do it by saying n times 0 is 0, n times 1 is n, and n times n is 9 of n times n minus 1 plus n. That will work. And here you see what will happen if I apply this calculation from here above. And the key point is the special case should be the first one, and the general case the last one, because I have the first match pattern machinery in my head. In C++, it's different. Here I declare the general template. I have not implemented it. Then here I declare the partial fetish vectorization for n2 equal to 1, and here I do it for 0. So I have to do it in a different way. Sorry. What's also great about language like Haskell is in Haskell we have something available like lazy evaluation. That means the values will only be evaluated in case they are needed. So you can define data structures for infinite data. You can define algorithms, or you can work with infinite data structures, which is great to define it. And at one time you only say, I want only to get the first 5%. But you can define an algorithm which will produce you all prime numbers, but it will take a few seconds, of course. And of course you can save time in memory usage. In case you don't need to resize, doesn't matter. It will not be evaluated. Lazy is great in Haskell. Have a look here. I will calculate the length of this list consisting of 4 arguments, and you see 1 divided by 0 should give an error. In languages which will evaluate that eager, that's the opposite to lazy, that will throw an error, because 1 divided by 0, you know what will happen. In languages like Haskell, that will work, because to calculate the length of this, you have to know what 1 divided by 0 actually will give you. That will work in Haskell. That will not work in either languages like C++, Java, Python, and the most other ones. There are 2 exceptions of the rule. The new size of operator, which is part of the new C++ 11 standard, can accept variety templates, and that one will actually not evaluate it. That will work. But normally it will fail because C++ is an eager language. That means in case you invoke in C++ function f with argument ABC, ABC will be evaluated. So, here are my last 2 slides. This is a little bit more advanced. Here I'm defining a recursive function. You can see it only if looking at the pattern, there's recursion going on and there's no end condition. This will give me all numbers, as you see it here, beginning with 10, 11, 12, because I say successor of 10 equal 10 and add the successor of 10 plus 1. And 10 plus 1, of course, is defined in the same way. So you get a recursion and you get an infinite data stream, beginning with E and ending with Control C. But doesn't matter. I can say I want only the first 5 guys of this infinite data stream. That works in languages which will evaluate that in place. That will not work. And that's what will stop. Never. And now have a look. I think that looks a little bit crazy for you. But you can read it. That works in Haskell. The point is function composition. And I'm declaring here a function of that let each argument to the power of 2 filter all odd arguments out of the list, and doing it as long as the arguments are smaller than 1000. I'm declaring in place a new function by combining 3 existing functions. You know, programming in Haskell is like playing Lego. That fits. That's just great in this language. I'm declaring here a new function. And here you see, that's only an example for infinite data stream. This is a data stream beginning with 1 and will never end. We give you all natural numbers. And now I can say I want the odds of all numbers describing this infinite data stream, and that will stop because here is my end condition. That is also not possible in Python, but in Haskell you can do it. So you can write, if you are used to it, that's like reading a book. You read the text and you know what's happening under the hood. Apply, you know it from before. I show you another example. But to be honest, in C++, there's a special case of short lazy evaluation available, which is called short circuit evaluation. That means in logical expression like here, it doesn't matter what one divided by zero actually gives you, because this Boolean expression is true, so you have to evaluate the rest. Short circuit evaluation. And now, my last slide. What's missing in C++11? What's not possible? I will not say it in such a negative way. What's not possible? Here in Python, you have this comprehension, which combines of an extremely elegant way. I will call it the sweetest kind of syntactic sugar, which combine map and filter, which you saw before, of an extremely convenient way. That's also the Python way to do it. Not using map and filter, using this convention. This is of course for testing. This convention. What I want to do, I want to go over this list of two strings, and what I want to apply, that's my map function, is the first element should be the original element, and the second element should be the length of this argument. So I get a new list, only 4 and 4, 3. That means this is the map function. I get a new list, applying len s to all elements of this range, and creating in place a new list. That's extremely powerful, it's extremely convenient. Now I can also add a condition at the end, means a filter, because that's only syntactic sugar for map and filter, and I say, give me, here I'm iterating over all elements from range 11, means all elements from 1 to 10. I'm only interested in that one that are divisible by 2, and what I should do is E times E. So I get, you see it, 0, 4, 6, 8. No. I think that's great. But what you have in Haskell is function composition. What's also great. And because you can program like Lego, because the things fit together. Because in case you're working on lists, one guy will return a list, the next guy will accept the list, so that works. Have a look what I will do here. Here, extremely simple. I want to sort this list in a different order. Sorry, the descending order. Sort, of course, will sort it in the ascending order. Means 1, 2, 3, 4, you get it. I will do it in different order. What I say, I create in place a new function, sort, combined with reverse. And that function will do it, a new function. And that's the function composition. You know, from mathematics. And now my last example, because it's maybe it's the most difficult one, so it's okay. Here is the idea. I have a sentence, like here, a sentence full of titles. What I wanted to have is the longest title. That I want to achieve. Here it will begin and here it will end. Read it from the right, and I will end at the left side. So, at first, give me all titles, sort them by comparing lengths, reverse them, and give me the first one. This is the description of the algorithm I want to apply, and that will work. You can combine them because that works. And this kind of programming, I think, is great. You can express with a few things the whole intention. And in case you can read it. I'm interested in all titles. I will sort them by length. Then I will reverse the order, and I will get the first one because I want to have the biggest one, the longest one. Then I have only to give this defined algorithm an input, words, words will give me all words. So after this words invocation here, I have a list of words, and I can give it to my algorithm, and he knows what he has to do with words. So that was all.
What is the actual algorithmic complexity of this function? Because if you do it in C++, it's linear. If you do it like this, it's NLN.
Actually, I don't know it, to be honest. I don't know it.
Because you have to sort with NLN, and you have to reverse it in linear term, and you have to select first.
I only want to show you how you can combine them. I don't think about the complexity and such problems. Of course, we have to analyze the algorithm, but in Haskell there are a lot of tools available for analyzing this. It's a great platform to do that.
You can simply stay on that slide. It would be interesting to think about how close we can come with C++11 to that syntax. If we reformulate standard algorithms as objects and overload some operators to implement composition and stuff like that, or use the new syntax organization to mimic some list comprehension or something like that.
Oh, I don't get it. I get your question, but I don't get the answer. Any guess?
Have you come across the FC++ library?
Sorry?
FC++ library.
I know it, but
that gives you weak operator overloading tricks, the list comprehension syntax.
I mentioned one for F, C++. Yeah, a function library is written for C++. Correct?
That gives the answer to your last question. That gives you that syntax.
So you know what you have to do? Study it and give a talk next year.
And I'd also like to mention the MetaMonad library, which gives you a monadic framework for template metaprogramming.
What's the name of the monad?
It is called MetaMonad. It's a metaprogramming library which gives you
which language? Sorry?
C++.
Oh,
it's a C++ template metaprogramming library which gives you the do syntax for monads in template metaprogramming.
You should give this talk. So that's you.
Up to what complexity does the compiler actually support? So if you, for example, go back to the factorial example, you let the compiler calculate the factorial of 120. Does it support that? Will it error out if the recursion goes to B, or does it do more than C++ compilers?
Do you talk about template meta function?
Yeah, in C++.
That will not go. I don't know the boundary, but it will not go.
You will run. The int will run out very fast.
Yeah, I know it. I don't know the exact number, but I know it will happen.
The standard says 2023. It's a deep block.
Okay, 2000 or something should be enough for most operations.
In function language like Haskell, you have something like called end-recursive functions, which will make out of a recursion a linear problem. So it will succeed.
More questions?
Good, I'm done.